Buenas tardes a todos, bienvenidos a otro evento del capítulo regional de la Acoustical Society of America, llamado Spanish Speaking Acousticians in the Americas. Bueno, como siempre vamos a tener una información inicial del capítulo. Em, Como sabrán, este capítulo regional tiene como misión la de congregar a los interesados en la acústica y el sonido, principalmente en el área geográfica de América Latina y que hablan español. Y la finalidad de este capítulo es actuar como nexo entre la Acoustical Society of America y nosotros, los hispanoparlantes, que estamos interesados en estas temáticas. Hoy por hoy tenemos una membresía de alrededor de 329 miembros, que están repartidos en 4 continentes, en 30 países, siendo los más numerosos en Colombia, México y Estados Unidos. 49 de los miembros de nuestro capítulo son miembros de la Acoustical Society of America y tenemos membresía en 14 áreas distintas, áreas temáticas, técnicas de la acústica, ¿sí? Siempre queremos tener diversidad. Y 97 de nuestros miembros son estudiantes, que siempre nosotros bienvenimos mucho a los estudiantes. Para unirse al capítulo es muy fácil, es gratuito, hay que seguir el link que está en pantalla. Y si alguno de ustedes quisiera involucrarse con el capítulo, son cargos ad honorem, en los cuales voluntariamente se colabora con el capítulo. Pueden escribirnos un email a ese email que está en pantalla y podemos ver de incluirlos en la junta directiva. Para asociarse a la Acoustical Society of America y tener más participación en la sociedad, hay varias maneras de hacerse socio. Una es lo que se llama, que es una forma nueva, que se llama el CIE Associate, que es para personas que viven en países en desarrollo, que esto incluye todos los países de habla hispana en Latinoamérica, y el precio es de $50 por año. Un precio muy atractivo. Pues los estudiantes tienen una categoría especial que cuesta $50 por año. Ser full member, que permite tener todos los beneficios de la membresía y votar en las elecciones de la Acoustical Society, cuesta $200 por año. Y también hay otra categoría que es Associate, que tiene los mismos beneficios que el full member, pero sin derecho a voto. Y vale $150 por los primeros 5 años y luego $200 por año. Esta es la junta directiva. Los que estamos abajo somos member at large y los que están arriba tienen cargos más específicos. Los member at large colaboran de una manera más eh, informal en el capítulo. Los que están arriba tienen una función más específica. Estas son nuestras redes con las cuales se pueden conectar con nosotros. Tenemos Facebook, LinkedIn, canal de YouTube, Discord, etc. Y bueno, ahora voy a cambiar al inglés. It's a pleasure for me to introduce to you Jonathan Broyles. He will give us a presentation on sustainable low carbon architectural acoustic design. It's a very interesting topic that lies in the intersection between civil engineering and architectural acoustics. So I will give you a background of Jonathan. Jonathan is a recent, he obtained his PhD in architectural engineering from Penn State. He was one of my classmates at Penn State. And he's an incoming postdoctoral researcher at the University of Colorado at Boulder. And he's studying embodied carbon emissions in buildings. His research interests are at the intersection of building acoustics, sustainability, structural engineering, and computational design. Jonathan is an active member of the Sustainable Acoustics Subcommittee under the Technical Committee on Architectural Acoustics of the Acoustical Society of America and the SE 2050 Committee under the Structural Engineering Institute at the American Society of Civil Engineers. So the idea of this group is to provide design guidance for reducing building-related carbon emissions. So welcome, Jonathan. And without further ado, you can start your presentation. I will stop sharing here.
Okay. Well, thank you. Thank you so much for having me. I'm going to go ahead and get the slideshow on. you guys should hopefully be able to, we'll switch this, should be able to see the slide deck. So yeah, so good afternoon, or good morning, or good evening, depending on where you are. I'm happy to be presenting on sustainable, low carbon architectural acoustic design to you today. So again, thank you, Fernanda, for the invitation. So a little bit of an overview of what I'm going to be talking about with you guys today is I'll give a little bit of an introduction on what I mean when I talk about sustainable design and low carbon design. I'll then discuss a couple low carbon pathways for acousticians or acoustic engineers, whether that's through like structural systems or building elements, building materials, and even systems, including like mechanical systems or the facade or building envelope. I'll then talk about what life cycle assessment is, what exactly do I mean by LCA, and then how we actually can use this method on a case study looking at floor assemblies. And then finally, I'll just kind of give a few overarching takeaways from the presentation. So I don't know where your background is with sustainable design. So you might be really curious on what exactly do I mean when I say sustainable design? And sustainability with regards to the built environment really aims to reduce the negative impacts on the environment, the health and comfort of building occupants or people, while ensuring an economical design. So sustainability, as you can see here, has three core pillars, which is essentially known as the triple bottom line of the three Ps to help the people, help the planets, and to gain a profit. So I first want to mention that acoustics, the really acoustic consulting, was known to be a sustainable practice because it benefits people. So people having acoustic problems, would obviously want to talk to an acoustician to make sure that people aren't inadvertently affected. But by and large, a lot of people are now talking about the planet or are really focusing on decarbonizing the planet, and not to disregard people or profit, these other two P's, but there's a bigger push on trying to reduce building carbon emissions. And that's really because the building sector, and specifically the architectural, engineering, and construction industries, contribute between 35 to 40% of global carbon emissions. And I don't know if you are aware, but there's a pretty big global climate crisis. So, as building designers and as practicing acoustic engineers, we have to figure out ways to curb the carbon emissions of our buildings. So to break this down a little bit, building carbon emissions are typically categorized as operational carbon emissions and embodied carbon emissions. And what I mean by that is operational carbon emissions are associated with any carbon emission connected to keeping the building lights on or keeping the building in use. So keeping the mechanical system running, having the lights on, and typical day-to-day operations are kind of categorized as operational carbon emissions. Embodied carbon emissions are essentially the carbon emissions from the material extraction, transportation, and the manufacturing of building materials, such as concrete or steel or wood, or even like plastics and some other materials. And typically the contribution to the total building carbon emissions is there's about 3/4 or up to 75% of the carbon emissions in a building is connected to operational carbon. The remainder is essentially associated with embodied carbon emissions. Now, especially in places where we're progressing towards renewable energy sources, so having greener electrical grids, it's projected that the contribution to embodied carbon emissions is going to change, and that the embodied carbon emissions will actually be a bigger piece of the pie, so to speak, because operational carbon emissions are going to be, in quotes, greener. So again, as designers, we have to be aware of trying to reduce both operational carbon emissions in addition to embodied carbon emissions. So I know that's kind of technical early on, so I'll present this a different way. So when we're looking at the carbon emissions over the span of a building's life, so you're looking at this plot, we have the year of a building's life on the x-axis and the annual carbon emissions on the y-axis. You can see that there's a very large amount of carbon emissions at the very front of the building's life. And that's correlated to the embodied carbon emissions, or this upfront carbon cost of a building. And that's in yellow. Then we have, excuse me, operational carbon emissions that are essentially trying to be, or that are happening every year, that they're annual emissions, and they decrease throughout the building's life with the expectation that electrical grids are going to decarbonize in the coming years. And then you have additional embodied carbon emissions later on, and the year 15, year 30, depending on how much maintenance is needed in a building. But typically speaking, we have a lot of different carbon emissions that we have to consider in the design of a building. So I kind of touched on this a little bit, but there are carbon dioxide emissions produced at every building life cycle stage. And typically when we think of reducing carbon emissions in buildings, we're focused on the operational carbon emissions. But in reality, we have to think about the materials and the products that we're using as well. Hi, Fernando. Did I get cut off? Hopefully not.
You did not. You did not.
Okay, perfect. I just saw a little blurb come up, but okay, good. So essentially what I'm trying to say in this figure is we have to consider all of the different life cycle stages here when reducing carbon emissions in buildings. So why does this matter? Why does this matter specifically to acousticians and other practicing building designers? And that's really because acoustic related design decisions can affect the carbon footprint of a building, whether that's how we specify building finishes or different floor assemblies, or even specifying acoustic baffles in certain places, or even, again, the design of our HVAC system. All of these design decisions actually have carbon consequences, whether they're good or bad. So we have to be very aware of what that carbon footprint is related to those design decisions. Furthermore, and actually knowing that this is, I'm talking to a worldwide audience, this isn't exclusive to North America, but there are many cities actually requiring LCA's life cycle assessment. So cities and municipalities are requiring carbon calculations to actually help that city or that urban area reduce carbon emissions. So cities like Vancouver in Canada, or Portland in the United States, have these policies in place actually requiring designers to quantify and then reduce the carbon emissions in their building designs. And this is starting to trickle into building codes as well. And that's very important, because if we don't know what to do or how to reduce carbon emissions, or even how to quantify carbon emissions, we're going to be left behind. So I'm now going to shift gears a little bit, given that motivation, to just some practical strategies. And I know these are a little bit more academic, a little bit more innovative, but strategies and pathways to actually reduce embodied carbon emissions and operational carbon emissions in buildings. So I'll start with strategies to reduce embodied carbon emissions first. And those include just innovative, I would say, building elements or structural systems, including green roofs. I'm sure people on this call are pretty familiar with green roofs. Mass timber building structures are becoming very mainstream across the world. And even geometrically optimized elements are a strategy to reduce building embodied carbon emissions. Moving on to operational carbon, designing very efficient, or really carbon efficient systems, including high performing building envelopes and even optimized mechanical systems, is a pathway to reduce our operational carbon emissions. There's also this kind of mix of benefit when you're actually specifying sustainable materials, and that could be material optimized structures. So again, really into the material science of a specific construction material, actually specifying greener conventional construction materials, and even using natural, especially local biogenic materials. That's a very good pathway to reduce the carbon emissions in your buildings. And you can see, depending on what type of pathway you select, that has a direct effect on how well you're absorbing sound in a building, how well you're blocking, or what type of controls do you have in terms of the acoustic system in your building. So now I'm going to kind of dive a little bit deeper on a few of these, and I'll start with just some innovative structures first. So I'm showing a plot here where we have several different structural elements or building systems for different construction materials. And you see concrete, steel, and wood here on the x-axis, and then their associated embodied carbon emissions on the y. And it's very clear when looking at this, concrete structures have very high embodied carbon emissions. However, wood structures have significantly lower embodied carbon emissions. So that's one reason why you might have been introduced or have seen, in your own country or in maybe neighboring countries, that mass timber floors are becoming a very mainstream solution to reducing our embodied carbon emissions in buildings. So that's something to obviously be aware of, because we know as acousticians, mass timber floors, especially when there's no other material layers applied, don't exactly have the best acoustic performance. However, it's a very sustainable design solution. Looking back at this, though, another pathway is to actually optimize other structural systems, including concrete systems. There has been a lot of research actually on optimizing the shape of concrete structures or concrete elements in buildings without sacrificing their structural integrity. So you can see on this these pictures here, this is actually a 3D concrete printed floor slab that was implemented in the design of a building. The benefit is that you have a lot less concrete in your floor than you would when you actually compare that to a conventional concrete system, thereby reducing the embodied carbon emissions. I've also looked at this quite a bit, quite extensively at Penn State in my PhD, where I can shape different ribbed floors to not only reduce embodied carbon emissions, but also improve the sound installation performance. So looking at the plots on the right, you can see here there are 3 different shaped floors that I'm highlighting that have low embodied carbon emissions, but higher sound transmission classes, so higher SDC ratings. And you can see on the table on the left, compared to conventional systems, we can get a really big gain in acoustic performance or a higher change in the SDC rating. But depending on how much SDC increase we need, that could have an effect on the embodied carbon emissions. So there's a trade-off here when you're actually trying to reduce the mass density of a floor system, which can also affect the stiffness, can also affect the damping of a floor, that thereby affects the sound insulation performance. So you have to be very aware when you're doing this pathway, and I know this is more scientific, more advanced, when actually specifying these optimized floor systems in building design. And I know I was kind of hinting at, I know these systems aren't super mainstream yet, but there are tests being done, and I've done some of them. There's also startups that are actually coming out with these types of floors that can, again, reduce the carbon emissions of a building, but can sometimes have a benefit to the acoustic performance, but can sometimes inadvertently affect acoustic performance. So again, as designers, we have to be pretty aware of this when we're implementing them in building design. Moving on to material pathways, I've talked a lot about concrete. I've done another study and actually just looked at the corresponding embodied carbon emissions of different concrete strengths And you could see on this box and whisker plot here that I'm showing that as you increase in strength, typically you have higher embodied carbon emissions. So you have to be aware when you're specifying concretes, how much strength is needed. Is this a structural floor, or is this a topping layer that you put on another assembly? That can very much affect the embodied carbon emissions of your building. You can also implement alternative concrete mixes, and I'm highlighting a very academic study where this researcher used this porous concrete mix that actually had benefits or sound absorption benefits in buildings. But there's many of examples of using lightweight concrete or even these different fillers in concrete to actually improve not only the carbon footprint of that concrete mixture, but acoustic performance as well. So something to be aware of, look to see what type of concrete mixtures are available in your local region and see if they can do something a little bit unique to actually have an acoustic benefit in your building design. So stepping away from concretes, natural, local biogenic materials can really help reduce the carbon footprints in your building while also improving the acoustic performance. And some of this isn't new to you guys, or hopefully shouldn't be. Using construction materials like straw bales or compressed earth blocks, even cork and hempcrete can all have benefits when reducing the carbon emissions in your building while also improving the acoustic performance, like having maybe higher absorption in your building per se. So definitely look to try to implement these. And I know it could be very much case dependent. Maybe you have a residential building, natural local biogenic materials might be a great option for you, but other maybe multi-story buildings, maybe it's a little bit harder to implement this strategy or this pathway. So one important trade-off when implementing, I would say, local biogenic materials is that sometimes there are construction limitations with these. There's also degradation issues, meaning depending on if there's like, if it's potentially in a fire-prone area, or if there's a lot of like water that it would be exposed to. These are things to very much be aware of because that can ultimately affect, the life safety and the quality of your building. So obviously very much an important thing to consider when you're designing in a building. Not only do you want something that's low carbon and acoustically viable, you want to make sure that the material is safe and that there wouldn't be any life safety consideration with it. Moving on to systems, I mentioned high performing building envelopes, and that really actually comes down to windows. So if anybody is familiar with double pane and triple pane, which hopefully there are a few consultants here on this call that are more familiar with those types of windows, there's not only an acoustic benefit, but there's a pretty big operational carbon benefit as well. And this chart is pretty insightful. Higher performing windows can really, it almost gets to a net zero type of operational carbon emission because you're balancing this solar gain energy with the heat loss from that window. So very high performing windows can be an awesome solution to reduce operational carbon emissions while also having a good acoustic solution as well, because there's generally better sound insulation when you implement those versus like a single glazed window or single pane window. Now, the trade-off with these types of windows or higher, more efficient envelopes in general is there's generally a larger upfront cost connected or associated with windows or even like better, more energy efficient mechanical systems. There's also potentially more maintenance involved with the upkeep of these types of systems as well. So you can see here pretty clearly, double and triple pane windows are a little bit more expensive. The double is not too bad, but the triple is when you really see a much larger cost. And then again, the upkeep of these can be very high, especially depending on how many windows do you have in your building design. Are they high end? All of that has to be considered when you're designing your building. So I'm going to pivot now after talking about all of these different pathways. And it's great. I think some of hopefully some of us are familiar with, or we're already familiar with some of these pathways even before this call, but hopefully all of us now have a few ideas of how to reduce building carbon emissions. But now I want to talk about how do we actually pick which solution, like which one is best and how do we know? So I'm now going to talk about, I'll give a short lecture, a mini lecture on what is life cycle assessment? What is this method? And then actually demonstrate using a life cycle assessment to evaluate different floor ceiling assemblies for both their carbon emissions and then their acoustic performance as well. Okay, so what is life cycle assessments? And maybe you've heard of it, maybe you haven't. This is kind of geared for the people who maybe are a little bit more newer to this, a little bit more green. But life cycle assessment is a systematic method for evaluating a product's potential environmental impact throughout its life cycle. So this is a method for actually giving a number to those embodied carbon and operational carbon emissions. Life cycle assessments can be applied to a specific building product. It can be applied to a building assembly, like a floor ceiling assembly, a wall, and it can even extend to a whole building. So you can do an LCA on a full building. So lots of different scales with this. Life cycle assessments almost always follow these ISO standards 14040 and 14044, which if you're not familiar with those, I encourage you to just look them up, reach out to me, and I can point you to those standards. But those kind of set the foundations to what a life cycle assessment is. It should be worth noting that there are several environmental impact metrics out there. I mentioned that LCA is a way to quantify these environmental impacts, but there are multiple impacts that we could quantify. Typically, though, for building designers now, we're most interested in global warming potential because this metric is typically used to quantify climate change, specifically global climate change. So what is global warming potential? I'll dive in a little bit deeper. Global warming potential, again, is this environmental metric that actually measures or quantifies how much infrared thermal radiation a greenhouse gas absorbs in the atmosphere over a specific time period. Now, that sounds very scientific, I know, but essentially the global warming potential normalizes what would be called this global warming effect of many different gases relative to carbon dioxide, which is used as the reference gas. So you will see in this environmental metric that GWP is measured in kilograms of carbon dioxide equivalents, so kilograms of CO2e. So that's essentially the unit that we're quantifying global warming potential to just gauge how bad to the climate, to global warming is our design. So what are the steps to conduct a life cycle assessment? The first is to actually determine the goal and the scope of it. So it could be maybe we're just focusing on understanding the carbon emissions associated with this floor ceiling assembly, or like I had mentioned before, maybe we want to know the carbon emissions of an entire building. So obviously a very different goal, a very different scope as well. And to that end, we have to also consider all of these different life cycle assessment stages. I'm not going to talk about them in detail now, but the premise is there are carbon emissions, again, associated with all of these different stages in a building's life cycle, whether that's the product stage, again, associated with like the material extraction, manufacturing, to actually constructing the building itself, to the building's use phase, and then end of life stages as well. So again, knowing what LCA stages you have to consider would be defined in the scope of your life cycle assessment. So once you define that goal and scope, you would then need to obtain a bill of materials. And I hopefully haven't scared people away of life cycle assessment. It's really not too bad. And I'll give you an example why. A bill of materials, for especially for like a concrete floor slab, is really pretty simple. If you're looking at a 150 millimeter concrete slab, the bill of materials would just be that 150 millimeters thick concrete slab. So pretty simple. This isn't too bad of a step, especially if you're just focused on like a floor assembly, for example. But even in this case, you could have more complex floor assemblies that would have larger bills of materials. For example, this mass timber floor has 102 millimeter thick concrete floor topping. It also has a 25 millimeter acoustic mat. And then it has this mass timber floor that's 175 millimeters thick as well. So you can see kind of quickly the bill of materials can really be extensive, especially if you expand the scope to like a full building per se. There would be a lot of materials and things you'd have to account for in that LCA calculation. So after you define the bill of materials, you would need to also obtain a life cycle inventory of carbon coefficients. And essentially what I mean by that is for every different construction and building material in your bill of materials, you would need to find a corresponding carbon coefficient. Now, for those unfamiliar with this, you might be wondering, how do I get these carbon coefficients? There are several public and open source databases. There's also generally a lot of public environmental product declarations for different building materials. So I'm showing here a screenshot of a ready-mix concrete mixture environmental product declaration. This is essentially communicating its environmental impacts, kind of like the nutrition label on a food product. You see the benefits, you see the consequences, so on and so forth. So just kind of highlighting here, we have the environmental impacts on the right for a declared unit of a specific type of concrete mix at this plant in Newark, New Jersey, in the United States. Then you have a description of what it does, and then the concrete compressive strength as well. Underneath, it's important to know what is the unit, the declared units of all of the environmental impacts. And then below that, you have a list of, this looks like 8 different environmental impacts that this EPD is providing. For our calculation, we just want to know the global warming potential. Again, the GWP, as that kind of, again, is used as the metric to quantify global climate change. So for 1 cubic meter of concrete, for specifically this concrete mixture, our global warming potential, or our carbon coefficient, is actually 460 kilograms of carbon dioxide equivalents per cubic meter. So after you obtain the carbon coefficients corresponding to materials in the bill of materials, you would then calculate the global warming potential. So for this example, the concrete floor example, we have the 150 millimeter thick concrete slab. We have this carbon coefficient of 460, and we essentially just multiply that. So per our, again, 150 millimeter thick slab, times that by the carbon coefficient of 460 kilograms of carbon dioxide equivalents per that cubic meter, which is the declared units, our floor assembly has a GWP, or an embodied carbon emission, of 69 kilograms of CO2 equivalent per floor area, per meter squared. So, and the per meter squared is nice is because that would essentially allow us to have apples to apples comparisons of floor assemblies, even if those floors had different areas. So hopefully that's clear to you. If not, I definitely welcome questions. But now I'm going to essentially demonstrate this on a case study looking at different floor ceiling assemblies that satisfy acoustic performance while also minimizing carbon emissions for a multi-story residential building. So this is in collaboration with the sustainability lead, Kristen Murphy at Syntec. We use life cycle assessment to evaluate 9 different floor ceiling assemblies. And you can see assemblies A, B, and C are all kind of these wood mass timber assemblies with different toppings and other layers. Assemblies D and E are more concrete-based assemblies where it's more of just kind of this structurally or this thick structural concrete floor, with assembly E having a few additional layers. And then assemblies F, G, H, and I are these steel composite systems with either additional flooring layers or even a hanging ceiling. So we looked at all these different materials and again had to find those bill of materials or material quantities in addition to those carbon coefficients to find the GWP or embodied carbon emissions for each specific assembly. And what we found was, depending on the assembly, different material layers and their thicknesses corresponded to different embodied carbon emissions. So on the left here, we have those same 9 assemblies. And on the right, we have embodied carbon emissions on the x-axis, or assemblies on the y-axis, and then the total embodied carbon emissions, but then also the distribution or the breakdown of each material's contribution to the total embodied carbon of that floor assembly. So what I mean by that is like assemblies A and D, which are either just wood or just concrete. Concrete and wood would then be 100% of the contribution of embodied carbon emissions for that assembly. So it should be pretty clear here, and we'll see it more later, that assembly A, which is just the mass timber floor, has the lowest embodied carbon emissions. You compare that to the assemblies like D and E, or even DE or D through I that use more concrete, and you can see that their carbon emissions are quite a bit higher. Furthermore, the percentage of embodied carbon emissions that the concrete is contributing to is significantly higher than anything else. You see that it ranges from a 50% embodied carbon contribution to even 78%. Of course, assembly D is just concrete, but concrete in and of itself contributes at least half of the embodied carbon emissions. So that's pretty interesting to note. Wood and wood decking is significant, but it's pretty clear looking at this chart that it's not of the same magnitude that concrete is. And then lastly, all of the underlayments and the channels, furrings, even the gypsum panels, they really contribute a very small percentage of embodied carbon emissions for each assembly. And you can see that could be in the range of like a couple percent to maybe 12% total. So a much smaller percent when comparing that to the embodied carbon emissions of the concrete or the wood itself. So I mentioned that we wanted to see what assemblies were both had low carbon emissions, but were also acoustically viable. So we use test data like acoustic lab data to plot their sound transmission class ratings, which is again quantifying the airborne sound insulation performance of these floors in comparison to the embodied carbon emissions. And it's hopefully pretty clear to you all looking at this plot. Assembly A, which is just the mass timber floor, has by far the lowest embodied carbon emissions. But once you kind of show this other, other design goal of having at least an STC above 50, it is the only assembly that doesn't meet that acoustic goal. All of the other 8 assemblies have an STC rating of, I believe, 52 or higher, with assemblies H and I, which have that drop ceiling, actually have a much higher STC rating. So, okay, so we know assembly A, definitely the most sustainable, but definitely not acoustically viable. When we actually look at these floors for impact sound insulation as well, using the metric impact insulation class rating, or IIC, we see that there are now only 4 assemblies that are acoustically viable for both STC and IIC. Those assemblies being assembly C, which is a mass timber-based floor, assembly E, which is a concrete base, which has a concrete base, and then assemblies G and I, which are steel composite systems with floor layers on the top. So these 4 floor systems would be acoustically viable, with assembly C having the lowest carbon emissions. So It's very different when you compare all of these scores for both carbon emissions and acoustic performance, because all of a sudden, what maybe would be considered for just sustainability or the sustainable goal, assembly A, would not be acceptable for acoustics. So now we would just consider assembly C, which would have the lowest carbon emissions, or assembly E, G, and I. And something else interesting to note as well. I'm talking about typical residential buildings here. So it has to have an SDC rating of 50 or higher and an IIC rating of 50 or higher. Assembly I is the only one that would actually be maybe viable for what I would say high quality or very high class residential buildings. So very upscale buildings would maybe even just want assembly I and have every other assembly and every other assembly would not be considered. So something else to note, you have to consider both acoustics and carbon emissions when actually identifying what system would be viable in your building design. So yes, so only four floor ceiling assemblies would actually be acoustically viable, but depending on your building needs, maybe assembly C would be best, or maybe assembly I would be best. So to kind of start to wrap this up, why do these results matter to me? Yeah, so building design is really being heavily influenced by low carbon design decisions. Again, trying to reduce that 35 to 40% of global carbon emissions. But, and what's important for us as acousticians to know, the lowest carbon solution might have poor acoustic performance. So we have to be very aware that we have to consider both of these design goals and that they can compete with one another as well. So point two, concrete assemblies, which we've noted, have high carbon emissions. So as designers, we have to know when we need concrete because sometimes it might just not be needed. So very much something to consider in the design of your buildings and your acoustic practices. Lastly, and I kind of maybe gleaned over this, but impact sound insulation in our case study was the controlling design constraints. So it's really important for practicing, acoustic consultants to talk to your architects, talk to your building owners, your clients, your other building practitioners early on, because then you can be a part of actually making sustainable decisions without sacrificing acoustic quality or without sacrificing other building design goals. So that is very important to remember from this talk as well. So yes, so now in summary, just a few high-level conclusions. It's imperative to reduce embodied carbon and operational carbon emissions in your buildings. Definitely start to leverage low carbon pathways in your design that also have acoustic benefits. And then start to apply life cycle assessments in your building projects, because that can help you determine what is both acoustically viable but also low carbon. So with that, I want to acknowledge Krista Murphy, as she was my collaborator with the case study that I presented on, and would also like to thank you for listening to this talk.
Well, Jonathan, thank you for this really, really great talk. I think it was, can you see me? Let me turn on my camera. It was very clear. Everything was well presented. So thank you very much. It's a very much a trending topic. And so I think it has a lot of application here for South America. It's something that it's on the top of the list for many designers. So thank you so much, and excellent presentation.
Thank you.
I will start looking at the Q&A to see if there are any questions.
Okay.
Here we have one from Zachary Italian. I believe that TJ is translating me as well. It says, in the case of mass timber, are there considerations for deforestation impacts in the LCA or other sustainability analysis? Yes, I was thinking about the same.
Yeah, and that's a really excellent question, first and foremost. Generally speaking, most, and I preface and I emphasize most of the forests that would actually harvest mass timber, like trees, essentially like the trees that were used to fabricate mass timber assemblies, are in sustainable forests, like sustainably harvested forests. That's not the case worldwide. So it's very imperative when you're actually designing a mass timber floor to know where the trees are being harvested and manufactured. So talk to those manufacturers. Oops, my camera just shut off. Um, talk to those people because a lot of them should have an environmental product declaration that would actually like specify, hey, this is sustainably harvested, or if they don't, maybe it's not. So yes, something to be aware. I would say if you're designing pretty much in the United States, but most places in North America, those forests are going to be fine. You don't have to worry about the effects of deforestation. That does change once you start to look globally, though. Yeah, great question.
Okay, here we have another question from Jose Manuel Palacios. He says, are there any low carbon LCAs, sorry, of new types of solution like acoustic black holes or metamaterials?
Oh man, yeah. It's just starting. I would say some of that research and the quantifying of the carbon emissions of those more advanced systems like the black hole absorbers and metamaterials. Um, yeah. So in short, it's not those results aren't known yet. I know a researcher here at the University of Washington in the United States that is starting to look into that. But generally speaking, like, and I have like a little prepared question. There's very little research actually done on quantifying like really innovative um, building and acoustic solutions in terms of carbon emissions. So not yet.
Okay, thank you. We have another question from Alejandro that says, how can we calculate the global warming potential? That was the name, no? Global warming potential, Jonathan?
Yep.
Yeah. Of materials that do not have it in their specifications. Yes. What would be the best alternative to achieve a balance between sustainability and STC or IIC?
Yeah. This is kind of almost a two-part question, it sounds like. Um,
Mhm.
One of the challenges here, like with architectural acquisitions, and this is something that, like, this is one of the research directions that I'm looking at and trying to address, is there's very little like databases that have all of the different global warming potentials of different acoustic products, and then how that would benefit the acoustics in a building. Um, there are some people starting to do that, but like having both acoustics and the GWPs. But by and large, it's very concentrated on like maybe two two projects. Really, that's part of the reason why like I was contacted from a Tech to like do this case study. And there's a lot of interest, and it's like you mentioned, Fernando. This is a topic that's growing rapidly, and something that has to be addressed. So both acoustics and GWPs, that's kind of it's in its infancy. Like databases of that are still kind of forthcoming. However, databases just on like generic materials are kind of out there, at least in terms of their like carbon coefficients or their global warming potential. The ICE database, which is more European focused, but can still have like it still kind of considers things globally a little bit. There's some caveats to that. It seems to the inventory of carbon and or yeah, carbon and energy. It's out of the UK, University of Bath. That would be a great resource if you don't have specifications for your specific building material.
Great, Jonathan. We have another question that was not on the Q&A, but on the chat. It says, great talk. Jose asked this, great talk, thanks. How do you see the greenwashing that is being done today by several material manufacturers?
Oh,
What to do to stop greenwashing?
oh gosh, that's a first and foremost, I'm glad you enjoyed the presentation. Yeah, there's a lot of greenwashing going out there, and very much so. It's driven by money. Is really what like the how people are talking about low carbon design is very much driven by who's paying them. So you see a lot of people talking about mass timber, but mass timber isn't the best solution for all building systems. That's why it hasn't been done. Concrete, same deal. There's a lot of people that are like, hammering concrete when there's a lot of really good strategies out there to have low carbon designs with concretes. Um, so yes, greenwashing is a problem. There's no really good way to kind of cipher through it until you start to become knowledgeable yourself.
Okay, great. Let me see if there's another question. I do have one, which I know that you're involved in LEED
Yep.
certification, and could you give us an opinion? We know that the latest edition of LEED certification has sort of downgraded acoustics quite a lot. I would
Yeah.
like to hear it from you. You're a person that is involved with this. Maybe you can give us some insights or what you think about this.
Sure. I'll give like so full disclosure, I'm not on any like code committee related to lead or related to well. I'm starting to get into some from like the structural standpoint. I think acousticians, we need people. Like I would very much welcome collaborations on this to kind of have a similar thing for acousticians because there's nothing like that right now. But yes, both with lead and with well's maybe a little bit worse. They're kind of not they're almost ignoring acoustics and acoustic benefits in buildings, which is really unfortunate and frankly just bad bad practice a little bit. It's in part because the science behind it, from what I've been told, the people who are writing these codes aren't really well knowledgeable acousticians, or they're trying to simplify this in a way that's palatable for like all building designers. But that kind of takes away from like acoustic consultants are the experts. We're the professionals. We should know what to do for different buildings and like what acoustic qualities are needed for those different building types. But the skinny is these types of codes, frankly, are maybe not really well advised on what they should do to this point. And the biggest push, and it's kind of driven by like governments and municipalities that have money, they're really trying to push the decarbonization stuff. Again, that's kind of the point of some of this. Uh, but that's to a detriment of actually making like the acoustic, parts of this code better. So I guess getting back to your question, Fernando, they're updating a lot to make sure that they have low carbon, essentially like goals in their codes. But yes, acoustics is not being well quantified and talked about in them. Hopefully that changes, to be seen.
Okay, I think we have no more questions. Is there anybody that wants to make a question to this great researcher we have here today? So take the opportunity. Don't be shy. We have some more minutes left. I think it's a wonderful opportunity to bring out comments or insights for our countries in South America, how you see what Jonathan presented, how it can be applied here in our countries. Is there anyone else that wants to make a question? Nope, seems no.
Feel free to reach out via email too. So
Yeah,
take that. Please reach out.
okay, it seems that there are no more questions on the Q&A. So, well, Jonathan, thank you so much. And this presentation will be recorded, but it has been recorded and will be available in our YouTube channel. So if you want to send the information to your friends, not Jonathan, but and the people that are connected, want to share this with friends and people that might benefit from this presentation, please use the YouTube channel where all the recordings of our events are stored. So, well, thank you very much. And thank you once again, Jonathan. And, well, Thanks everyone that was here today.
Thank you.
Goodbye.